everyone here that you expect to be here? Yeah?
So,
Ready to go?
Lean back chair.
Okay, so this is a recording I did a while ago. Does that look familiar to you?
no.
Okay, good. Make sure you already didn't see this one. So I think this is way back when this whole idea came up of me recording trainings for you guys and having you watch them. So I was going to try and give it live, but I've got a bunch of drawing links in the presentation, so I'm just going to play my recording and then I can pause it. We can talk about certain things. So that way I cover what I thought was important at the time, because I recorded it like 2 years ago. So hopefully it's loud enough. Where's the play button on the screen? Do I just click?
All the way at the bottom.
It's very small. We record this session.
Nice.
Called Interpreting Plans. So that the 105 FRP team in Vietnam could better understand how structural and architectural plans are drawn, or typical plans are drawn. Every consulting firm, whether it's architectural or structural, have their own kind of drawing standards that they adhere to, but for the most part, most plans are fairly similar. So I wanted to walk through a few of the example plans we've seen in the past and address some of the mistakes that we've seen through the NCR process for this. So I'm going to walk you through a fairly quick presentation here on interpreting plans. So with that, let's get started. Part one of the training will be structural drawings. This is from one of the projects we worked on that shows, I zoomed in here on a structural plan. So it's a top level plan of a 5-inch thick slab. You'll see the girder below is dashed, G2OB is dashed below. Beams framing into it are also dashed. And the way this is drawn here, you'll see indicates intersecting beams are of the same depth, meaning that there's no line between the girder here and the beam. That's supposed to mean that these are of different depth. Now I think on this particular project that wasn't the case, and so they did it incorrectly, but that's one of the signs that you can tell what depths are of similar elements. Let's say that the girder is deeper and the beam is shallower, there should be a dashed line here continuing through. And like I said, the edge of the beam below, the edge of the column below. If the element is dashed, that means it's below the slab. If it is a hard line, that means the element protrudes above the slab, so like to a bollard level or a rail height level, so a few feet above the slab. If this column was indeed a hard line, that means it extends up above the slab.
Did that make sense so far? Yeah?
Yeah, you maybe want to go
back
back to where it's up on the screen again. You can kind of reinforce.
So mostly looks like, except for these vertical lines on this row and here, pretty much everything on this plan is a dashed line, which means it's below the slab. You're on the top of the slab looking down. So this particular plan says that this girder is 20 inches wide by 34 inches deep. DP stands for deep. Yeah, and I think this slide came up as a result of an NCR at that time, where I think the designer didn't realize that the beams were the same depth. And the way it's drawn on plan, you can basically, the joist or beam can also be assumed to be 34 inches deep. So
the idea when you're looking at a plan view is that if it's a plan view of this floor, the picture that you're looking at is taken like 1 inch above the floor. So it's like a cross section cut right here. And so the dashed line with the break in it means that it's happening below. So you can't really see it, but it's there. And one of the things Brad said is if you have a column sticking up above the slab, I don't know if that's what that is.
Probably not. I'm not sure what that is actually. It looks like a curve with some sort of post on top or something.
Well, anyway, if you have something with a solid line, that means that it's sticking up out of the slab like a column or something. So that I think is
Yep.
one of the ways to tell where something is based on the plan view.
Can you guys hear okay? My recorded sweet voice? I must have missed.
8 feet above the slab, if this column was indeed a hard line, that means it extends up above the slab. So on AC Transit, another project we worked on, here's some drawings I pulled up. Basically, this is my old design firm, Audrey Design Group. I used to work there, so I know this style of drawing somewhat like the back of my hand, meaning I'm very familiar with it. So I kind of want to walk you through, this is a post-tension slab. So there are steel tendons draped, which means profiled. They go midpoint is where you stress. So this arrow here is a stressing end of this cable. It's at midpoint of the slab. You have to stress or have your dead end of a cable. Dead end is basically indicated by a dash here. So that's the dead end of this cable, and it's stressed out this edge of the slab. So this dead end and the stressing end are in midpoint of the slab. This is the low point at the mid span of this slab span, and this is the profile of the tendon. So this is basically from the soffit of the slab or bottom of the slab. The centroid of the tendon is 1 inch. And then at this high point, it's 7 1/4, then 4 1/4. So this is a shorter span, so it doesn't need as much profile or uplift. Back up high to 7 1/4, and then down to 5 1/4 here. So you can kind of walk through and see that the profiles of these cables. I should also let you know, when the tendons have this kind of extent line on them, those are called uniform cables. So these are spaced at a spacing in order to get an average compressive stress of 12.8 kips per foot of width. And so these are uniformly spaced along this slab edge, and they span over banded cables or groups of cables that are provided over the columns. And those have a total kips of 205 kips for this particular banded cable grouping.
So did you guys understand post-tension slab? This is a two-way slab or two-way plate, as it's called. And the banded cables act like beams, and the uniform cables act like a one-way slab, sort of. So it's kind of how you can relate the two together.
And so that all of this information, you could take the information from this and fill out the post-tension slab strengthening summary table. So the information on here includes the tendon profile. So the tendons go down at the midpoint and up at the support. And so that gives you D, your depth, or DP. And there's other stuff you can get. The post-tension force, right?
Yeah. That's about it, I think. Like you wouldn't be able to know friction loss and all that stuff.
But the force would be like the effective force, right?
That's true. That's a good point. Yeah, that's what it should be designed for after all the losses. So yeah, technically you could just put in that number. Yeah.
So this would be an example of a project where we might not have the questionnaire filled out, but you could read these shop drawings and or these drawings and tell what the conditions are.
Yeah, I don't know the questionnaire off the top of my head, but I think you can fill in most of it from this plan. You got it? Any questions? No? Okay.
So typically, at least at Watchery, we design cables to be an effective pre-stress force of 26.8 kips per cable. So you basically do the math. I'm not sure back in, when these drawings were created, if that's what they used, but when I was there, that's what they used. So, this symbol here is for top bars over the supports or over the columns. Usually there's a key on drawings. You zoom over here to the legend or key. This basically indicates what that symbol means. So this is the number of rebars, so nine bars, the size of the rebar, so 9 number 4s, and then the length of the rebar by 10 feet long in feet. And it indicates bottom for this particular element, so, for this particular call out. So I do know from my time at Watchery that these are top bars, even though they don't have a T here, because they're right over the column. So this is 8 number 4s, 10 feet long in each direction. So this call out goes for this bar, and this call out goes for this bar. One other kind of unique, tricky part is this hatched area here of the slab. The hatched area indicates depressed slab. So there's basically a step in the top of the slab, and that's what this symbol indicates here. This is the top of the slab, as if you're looking at it, and you tilt your head to the left. So your head to the right of the page looking at it. So this depressed slab is a 2-inch drop here. And then there should be that symbol over here as well, and over here. And then basically it should go all the way around, but wherever there's adjacent slabs. So that's what that means there. This dash line here is a wall support below. And then let's see what else. This particular hash pattern at Watchery indicates a CNU wall that extends up. And if there's no hatch in it and it's dashed, it means it's below the level. What else? This hatch pattern at Watchery means a closure pour. So if we were to go to this sheet, it would basically show they leave this section of slab out when they pour this section, and it allows the contractor to stress the cables in this block out. It also allows this portion of slab to shrink independently of this portion of slab, and basically it's better construction practices, and you get less cracking because of that as well. There's probably also, well, actually I don't see a construction joint on this slab, so it's small enough where they can pour this entire piece, the contractor can in one pour. There's a typical note like this, 8.5-inch thick post-tension concrete slab, typical unless noted otherwise. That's what UNO stands for. And then you see how this cable here only goes back for a certain dimension. That's basically added for this last bay. So it needed some, when they did the design, they needed some additional strength because this last bay is so long, and you're not getting the full profile, right? Your tendon profile is half at mid-height of slab here and at the top point here. Whereas this particular, while it is shorter, the span is shorter, you're getting a high point tendon here and a high point tendon here, and you can basically do this all the way to the lowest point if you want. So you can see this is only at 4 1/4, so it didn't need to get as much uplift there. So anyway, I know it's not FRP related,
Question?
but I think it's helpful for when you guys are looking for particular
Find the
rebar.
tiny pause button.
It's hot too, listen to.
It's hard to hear.
It's
Yeah.
So,
It is garbled, isn't it?
yeah. Would it help to draw some of the stuff up on the whiteboard? Like, I think a lot of the things are notes that we should recognize.
Mm-hmm. So how do you,
Sorry. I was just gonna, like, one of the things you pointed to up there was when you have a step in the slab, you would have a line that looks like that.
yeah, and also go back on the screen, which is really hard because it's so tiny. Well, you can see it right here. So there's hatching on one side of it. So the easy one to look at is the one that's like facing us, that one I just found. But that's, yeah, that works too.
So it would be like you have a line here on the drawing, and this would say like 2 inches. And so this slab here would be 2 inches below this.
Correct.
So if we were gonna do like top of slab strengthening, you would have to build like a paste ramp or something here to kind of go up that joint. What were some other symbols you were?
Let's talk about the tendons, the added tendon.
Yeah, so the,
Right, so I guess the worry would be on this. Actually, it's hard to see on this one, I don't, so, that is not my computer. Well, my computer had stuff on it, but I don't have Snagit, so we had to switch to Griffs, so. Should I just pull up this
AC
plan?
Transit?
Yeah.
It should be pretty easy to get to.
Where's the screen compared to that screen?
Left, it's backwards. Yeah, there you go.
Click on, scroll up and click on O1 projects, and then AC Transit, 20,
Do you remember?
20.
Well, I know where the,
2016.
should I not pull
pretty
them
old.
off the US drive?
It'd just be really slow.
Slow. I don't even know if those files were on the VM drive, because we did those ourselves back before we were doing. Yeah.
Tricky. Do an email search for AC Transit, or I mean, we could try the US drive and copy it over to the desktop.
Now that we successfully lost the group. Do you not have a link on your desktop?
Oh no, sorry, to get to the US, see it.
This one?
CSS. No, scroll down. Huh, sure where. Oh, click project support. That'll be in the CSS.
Oh, I see what you're saying.
Yeah. So one of the things we were showing on here was the tendon profile, where you have like spans, and they show in the middle. It was like
It's like 1 inch.
1 inch, and so this is the distance from the bottom of the slab.
Yep.
And then what would it be here?
7 1/4.
Seven and a quarter inch. So what this is showing you in the slab is where the tendon is. So here it's 1 inch from the bottom, so you're measuring up. And here it's 7 1/4 inches from the bottom. So your tendon profile is gonna look like this. So and usually does it end around the middle at the end?
Yeah, it has
You
to be
know.
at the midpoint. Either if you're not stressing right at the middle of the slab, then you'll impart a moment. It'll start spinning, or it'll want to spin.
Yeah, so you'd have, if it like went up to the top, then you would have cracking on the bottom.
Right. Yeah. Then you may blow out. I mean, you're putting in almost 27,000 pounds of force on a tendon. So if you're not in the middle, it might also just rip right out the top of the slab.
Dangerous.
Right.
But so for a slab like this, we might have an engineer give us the maximum positive moment here and the maximum negative moment here, positive moment here. So for our analysis, these would all be different cases, and we could get the depth of the tendon from here.
Going to the PT drawings slowly but surely.
I'll be able to copy the file.
There we go.
Oh, there you
All right. A little more interactive now. So here's the symbol Griff was talking about. It's a little easier to see at this location because it's facing you. But this slab on the left is lower by 2 inches. This is a 2-inch vertical step than this slab. One thing I'll kind of reiterate on this. These tendons say added. So this whole group of tendons is not whatever that says. Looks like 38 kips maybe. You have to find the note. See if we can find it. Here we go. So those 2 lines were 200 and let's say it's 85. I don't know what that is. Can't read it. And that group is the whole entire way. For that one, there's no added cables, but for this one, it's 38, let's say, plus whatever this is. So you have to add the 2 numbers together for the entire force in that last bay or span. So the only reason this added cable goes back this far is because it has to get down from the high point to the midpoint of the slab. So that way you get the full profile that you can get for that bay.
Is that because that span's longer?
Yeah, so typically if you have a long end bay, you have to add cables in that bay. You see at this bay it's really short, so they didn't need to add any cables there. What else did I say on the recording? I don't think much else. Was the reinforcement, the typical bars, was that clear, you think, or should I restate that?
If they give information about the length of rebar, does it include development length?
Yes.
So,
So what do you mean, does it include? Does it include rebar development length or FRP development length? Rebar, yes.
Right, so do we have to recalculate by the development length for FRP?
We
It's not the
usually
same.
extend it past, yeah. But
But sometimes we have to apply like 4 layers of CF44. It's really
really long.
right.
Yeah. Yeah, it's hard to know when we're doing rebar equivalents whether or not an engineer has taken all that into account, or they're basically giving us the exact length where they need the additional force. So we should always, to be conservative, always plan on extending it past that.
Okay.
And if it has to be 12 inches for the first layer, then 6, 6, 6, then it is what it is.
But
But-
when the engineer makes these drawings, they're including the actual length, right? When they show those bars, like that's the length of the bar they.
Yeah, so the rebar manufacturer, the rebar provider who's providing bars to go to the job site, looks at this project and knows he needs 9 number 4s by 10 feet long over this column, and so they're exactly 10 feet long.
Okay.
Yeah. But when we're doing rebar equivalency, we're not matching drawings that show what rebar was supposed to go in the slab, right? Typically. I guess that's it on this one. So I'm trying to think how I should do this now. Do we just like turn off the volume? And I guess what I said before and say it again? Maybe? I don't know. Seems a little weird.
You can make a subtitle.
Make subtitles? Yeah, I'll make it in Vietnamese. It'll be
Or,
great.
yeah, you can, play it.
And you're not getting the full profile, right? Your tendon profile is half at mid-height of slab here and at the top point here. Whereas this particular, while it is shorter, the span is shorter, you're getting a high point tendon here and a high point tendon here, and you can basically do this all the way to the lowest point if you want. You can see it's only at 4 1/4, so it didn't need to get as much uplift there. So anyway, I know it's not FRP related, but I think it's helpful for when you guys are looking for particular rebar. For an element, here's some bottom bars. Number 4 is at 19 or 19 feet long at 12 inches on center. Bottom, so then they get the limit line on where that is.
So do you guys understand when it's circled like this, and then it goes, and then, well, here there's an arrow here. So all of those elements are spaced equally for that entire width, yeah. That's so shiny I can't even push it.
Largo, so basically it's the entire bay, that's bar. These bars are more than likely stock at the face of this support here because this span is a lot different. And this one's even shorter, so even though the limit line shows all the way, we can pretty much bet that these bottom bars don't go into the elevator opening. Let me see what else we want to look at here. There's a north arrow on this, which is helpful. And then this is another partial second floor plan. I think there's a match line here. This is a match line, so the building from the previous page comes up to this point, and then this is a continuation of the page before. Now we should have a roof plan here, which is the top plan, all the same sort of elements called out. I don't believe, one thing I wanted to show you on a previous plan here. Find the correct drawing. So the previous plans we're looking at were the pre-stress plans or post-tensioning plans. And these are kind of the general structural plans that have other types of elements called out, like the diameter of column. This is the drop cap, so it helps with clenching shear. It kind of spreads the load out over a larger area instead of right around this 14-inch diameter column. You'll see because this column is hardline, it goes up to the next floor, while this drop cap is dashed, so it's only below. Typical sizes for drop caps are 45 inches by 45 inches by 8-inch thick. And the reason for 45 by 45, if you imagine a 4 by 8 sheet of plywood cut in half, so that's 4 feet by 4 feet.
I'll draw that. Oh, if I could stand up with my old Uncle Brad body. So it's kind of getting into the minute details a little bit, but so for a drop, you guys know what a drop cap is, right?
Remember
that
that vocabulary sheet?
A thickened portion of, and on this particular project, the column also goes up. So this is a thicker piece of concrete around the column, and this is typically, I think it's 7 1/4. So, and the reason for that is because they use typical sizes in the U.S. I think a 2 by 8 is 7 1/4, I believe, of wood, and then they have plywood underneath this. This is the formwork they use to pour the slab. And the plywood comes in 4 by 8 foot sheets. And so once you put all the formwork on it, it ends up being 45 inches by 45 inches in plan and 7 1/4 inch deep. I think in the recording I said this is 8, but it kind of depends there.
So the edges of the drop cap are dashed because they're below the slab, but the edges of the column are not dashed, solid, because they're above the
The second
slab.
column keeps going. Yep.
And one thing that you had said when this page was pulled up is that, like, this is a drawing for a floor in the building, and there's another drawing
That's right.
in the same drawing set for the same floor in the same building. But that drawing shows the post-tensioning details, and this drawing doesn't show the post-tensioning details, but it makes it easier to see other details, like the drop caps and the columns, right?
Yes. And that's probably more of an older way of drawing it. Like, I know the company doesn't do that anymore, but so for older drawings, it sometimes the drawing setup is different than drawings these days. So yeah, there's usually some description of what the plan is, which maybe this one has it. Which way do I have to go? There it is. Can't find it. So that just says second floor framing plan. This one does have a PS in the designation for pre-stress, and the other plans did not have that.
You could click on a ribbon, the left-hand corner.
The what now?
The
This
ribbon.
one?
Yeah.
Oh, baby.
So some of them say PS.
Right.
some of them
Oh
don't.
yeah, right. So these are all the pre-stressed. Thank you. And then these are all the normal structure plans, which we were looking at on this other. This way. No, this way. What are we? Where's it? Oh yeah, the cone.
Here's the traffic cone.
So this plan is the other set of drawings. There we go.
Feet, or 48 inches by 48 inches, and then the contractor used an 1.5 inch wide piece of a 2x material, basically, to form the edges of that drop cap. And so you take off an 1.5 inches, that's the actual dimension of a 2x number, an 1.5 inches on either side, so 3 inches total, so 48 inches minus 3 inches equals 45. This particular job has 2 number 5s over the top of the walls, pretty typically. We see the call out here, and then they're basically not drawing the entire length of 2 number 5s, but it still only needs to continue, it's just like you.
Yeah. So that's hard to see on that side screen. But what I was trying to say there is basically that those pieces of rebar are lines, and then they do a squiggle like that, which means they continue. They're not drawing the whole thing. So it's really hard to see right there where the hand is.
You gotta choose in your drawing. One thing I wanted to show you, I think on the next page. Well, maybe not, I think it's on the roof actually. There we go. So you see at the roof plan, the columns below are dashed, and the light pole base is a hard line. So this continues above this level, this is below this level only. And this light pole base is basically like a,
So can anyone guess what those arrows mean on the drawing?
What they were,
Yeah, what they represent?
circle lines, the circle one.
No, the ones with the arrows, the straight lines with the arrows,
Oh.
and then all of these
The
like diagonal lines.
Slope.
Slope, that's right. So this is a this is basically a roof slab of a building that you have parking on. And if you imagine if it was totally flat and it all rained, then the water would just build up. So this is basically a slope to drain, which I don't know if I talk about it, but anyway.
column that sticks up out of the slab to support a light standard, or a light there.
Is it me?
These are in
So I think that might be all
Oh,
for this.
probably it is probably Annika. You're right.
That, I don't believe there's anything else
I
here
just
like
like
the
that guy.
walkthrough. So back to the presentation. On the Ritz-Carlton project, I wanted to walk you through the rebar shop drawings as well as the structural drawings, show you what these elements mean. So these are the rebar shop drawings. So these are made by the rebar subcontractor. That he basically or she will use the structural drawings from that project. So basically, similar to what we do with our FRP shop drawings, we do what's needed to be done for our branches to price the job as well as the contract to install from. And so that's the same thing, same idea for rebar shop drawings. They detail every piece of rebar, all the shapes, where exactly they're needed to be installed. And they have basically a takeoff as well, so they can add up how much rebar material they need to provide for that project. And this is provided to the EOR or engineer of record to check and make sure that the rebar subcontractor got everything correct. So they have the slab thickness, they have that,
Yeah.
they want 16 number 4s, 27'8" at the
Explain which part?
Just
reiterate.
The EOR's drawings and the rebar contract.
Oh, right.
shop drawings.
So, the drawings we saw previously were from my old design firm, and those were the contract documents, what we call contract documents. These would be equivalent to our FRP shop drawings, but these are for rebar. So another company interprets what the EOR wanted on his project or her project, and then the rebar subcontractor provides rebar shop drawings that then, just like ours, go back to the EOR to review to make sure they interpreted them correctly. So they go through the same process we do. Is that what you're looking for?
Yeah.
32-inch on center bottom
Yeah, I told that
Blade.
myself.
in this zone here, in this bay here, and this is the extent line. So it kind of walks you through exactly what is needed. Now, on this job, we were doing FRP just in this tiny zone here. And so that's why this is clouded. These are the things that you guys clouded over in Vietnam. With 8 number 4s at 12 inches on the center. This is the shape. They have spokes on the end. And then also here's some more bars here. Those were 2 number 4s here at 12 inches bottom. And the slab thickness in this zone is 9 1/4 inch thick. So you're able to get what you needed from this particular rebar shop drawing for your design. And these are the structural drawings that came from. 9 1/4 inch slab again. There was cables. So in this particular job, here's a more, I'll say, recent PT shop drawing, or not PT, I should say, structural drawing that calls out for post tensioning. These dashed tendons are uniform cables, and these hardline cables are basically the banded cables. So you see the 238 kips, that's a banded group of cables that run this way, 132 is this group, 185 kips is this group, and then these are called out 16 kips per foot. So that's your sign to what cables are uniform, if they have kips per foot, and what cables are banded as a total kit. So you round basically, or you don't round, but you provide an equal number of cables, or a whole number of cables for that particular band. These engineers draw their stressing ends extending out beyond the edge of slab, whereas the washer ones you saw before had the arrow right at the edge of slab. A little bit different drawing conventions, but similar idea. Again, these don't call out the units. This is the 4-inch low point for this particular cable, 2-inch low point for the banded direction. This is a 33-inch high point, so this must be in a beam. That's why it's got so deep of a, or tall of a high point, or a tendon profile there. And one thing here, this particular kind of rectangle here is a block out. So what they'll do is the contractor will provide a stressing area in the slab, because this arrow where the stressing end needs to be at midpoint of the slab. They need to provide an opening in the slab to be able to get the stressing ram into it and pull those cables at this particular point. So they must have been cables that were long enough. Typically, you don't pull a tendon longer than 100 feet from one end. So this is probably longer than 100 feet, so they have a stressing end on each end of the cable. So again, not FRP related, but I think it's helpful.
Yes, sir.
How they can solve the tendon in the middle of the span?
You provide like an opening. So the tendon comes out at the midpoint of that,
Yeah.
and then you put it's called a ram, stressing ram. You put that inside the hole, and you pull it.
Okay.
Yeah, you pull the tendon through. And that's all you're doing. You basically have a tendon that's not stressed yet, right? It's a certain length, and you're pulling it. The contractor will literally take a piece of spray paint, paint that's in a can, like aerosol,
Yeah.
spray paint, and they'll mark the cable where, let's see, how does this work? They'll basically mark the cable where they have to stress to, and so they'll basically pull to a certain length, and when they hit the paint mark, they know they're right about where they need to be. And so you're basically stretching that steel. So that's what a block out means, just like this. They just pull it up.
Pretty good.
Sorry. And I guess one thing, when we were talking about shop drawings versus contract documents, is both these drawings we're looking at now and the first drawings we looked at are post-tension contract documents. So the engineer of record made those post-tension drawings, but they are not the post-tension shop drawings. So a lot of times we can get the post-tension contract documents from the engineer, but maybe we don't have the post-tension shop drawings. So the shop drawings give more detail, just like with projects where the engineer says, you know, put FRP here to resist 50 kips. Well, that doesn't tell you what to install, so our shop drawings say, put 2 layers CUC at 44, exactly where it goes. Here, on these contract documents, the engineer's done the calculations to say we need 34 kips of post-tension force, but no detail about how to get the 34 kips of post-tension force. So the post-tension shop drawings will say use 5 half-inch cables, stress each cable to this amount of stress. And then the same thing with the rebar shop drawings Brad was showing before. The rebar shop drawings show where every single stick of rebar goes. It's highly detailed, whereas the engineer's plans are less detailed. So the engineer of record does the overall calculations, but the rebar subcontractor or the PT subcontractor or us, the FRP designer, will do more detail because they know you have somebody who actually does the installation, do some of the fine design work.
Nice. Yes.
I have a question. Why they show 2 different type, like different units?
Yeah. So one's for the uniform cables that are spread out equally. So they give the amount of force average per foot. And so then, like Griff was talking about, the PT supplier will then do the math to figure out how many cables they need at what spacing to equal that force. Whereas the dark hard lines on this one are total kip, so that's a banded group. So you put an equal number of cables in that zone over the columns to act like your beam. And so you've got an even amount, or I shouldn't say even, you've got an exact amount of cables, like 5 cables. So depending on the force per strand, that's a total number of or a total amount of force. So that's the difference between. It's a little confusing, but on this one, the hard line is like a beam right at the column, or banded cables right at the column, and the dashed line are the uniform cables, the spread out. Yeah.
Nice to know. Or know these types of things. Learn some other things about other types of structural drawing. I don't believe there's anything else on these plans. Actually, this particular one has a 10th floor rebar plan, and then it's got some framing at the canopy, so that I believe this is the rebar plan for kind of the main portion of the building, and then this is a canopy that probably is over a porch or patio, maybe, and this is the canopy frankly over that potentially. I'm not exactly sure what the floor level this is compared to this. Maybe it's the same elevation. So anyway, so speaking of elevations, oh sorry, I have another thing here on structural drawings. This is one that a particular NCR where the team members in Vietnam thought this was an opening because they saw an X here. So we have to pay careful attention to because not all design firms draw the same way. This one, it does have a note called out specifically for this X. You follow over here, it says this is a 2 1/4 inch depression. So it basically is a 9 1/2 flat plate. So that's basically a slab, a 2A slab. So it's 9 1/2 inch thick, but it's a 2 1/4 depression. So what this zone means is that it's just depressed down. So I think on this particular NCR, we actually needed the FRP to be in this zone as well, but there is a top step, so we basically needed our pace ramp
makes
so
sense.
what I was talking about for architectural drawings, for 2 of the trainings, we don't really need to look at architectural drawings too much, except to figure out like heights of columns or heights of walls that we're strengthening. So you'll typically find top of slab elevations on building sections on architectural drawings or wall elevations, and that's pretty much all we need architectural drawings for what we do for FRP or FRCM design is top of slab elevations. There are some structural drawings that will call out top of slab elevations, but typically those are on architectural drawings. And so on another, on Snowmass, on a project we worked on as well, again, we had a partial wall elevation here and large elevation that had top of slab elevations called out. So you guys use that quite a bit to find out heights of elements for takeoff purposes. So that was all I had for today. I think that
Alright.
covered a lot of the.
Good job, Brad, Junior.
Do you want to go back to the depression things to make sure? we
Sure,
have that?
if I can find it. So easy to read that, isn't it?
So and this is different from the first drawings that you showed from Washery.
So use
Have a different detail for depressions, right? For steps.
Right. So I'm trying to think. So basically this looks like, if you're just looking really quickly, it looks like an opening. But there's a bunch of information also in here that will give you a clue that this is not an opening, right? And there's literally 2 leader lines that lead right to a note that says that it's depression. But you probably didn't know what depression meant. So.
Nhưng mà ngày xưa là từ cái đó là đâu mình lên
Gạch chéo á.
cho cái đó nó có hình cái vuông mình chia sẻ bên gì đó nên đá mà nó đi nó làm cái vùng những vệ sinh hay gì đó nó depression số 2 một cái cho nên là mình có chạy thẳng vào được. Okay.
So on the previous drawings we were looking at, that's where Griff came up and drew this symbol.
Okay.
So, same way.
But
Which
if you-
means the same thing.
Yeah, if you Google translate depression, it means sadness.
Right.
So it's not like the best.
It's
the
a sad
best thing
slab?
to directly translate. But to depress is to push down, like press, and then D is down, so press down. So 2 1/4 inch depression means the slab is pressed down 2 1/4 inches. And in the Watchery drawings we looked at earlier, the design firm decided to use a diagonal line over the slab that was pressed down. And this design firm decided to use an X over the space that was pressed down. So different companies can choose different drawing styles, which is frustrating because not every drawing is going to be the same, and sometimes you have to look very closely to see what somebody means by what they draw. And then in the architectural drawings that Brad was showing us, I think we talked about that in the NCR discussion the other week, that sometimes you need to look at architectural drawings, but normally you don't. Ideally, everything would be in structural drawings, but the biggest reason to look at architectural drawings is for dimensions. And specifically floor heights were the ones Brad was showing us.
So I have another 27 slides, but of the stuff that was on your cheese list. Do we wait for next?
Yeah,
session for
we
that
have
one?
we have it planned out to do structural drawings tomorrow too, so
Okay.
maybe we just start that one tomorrow.
Perfect. And this one will be better, and it'll be live. And the room will be set up, hopefully.
Okay.
Okay. That's it. Any other questions before we?
Có là gì không? Còn hai cái file xem nhưng mà cái phần kia đấy, cái phần này cứ
So for the project tomorrow, GSA project, what would it get?
Which one?
GSA project.
Oh, okay. Yes.
So can we take over it
Together?
Yeah.
Look at something together?
Yeah.
I'll give the
Yeah.
control back to you. Or just want to switch chairs.
Sure, we can switch.
That's pretty easier, I think.
Should we keep recording for
Oh,
this?
no. Good question. I don't know. I guess keep it up for now. We can always hack it later.
Maybe we'll learn something.
Whoa.
We have fun chair.
I know. Is that, it's different?
That's
Fancy.
Which, what's it, do you know the name of the project? Berkeley.
Berkeley High School, yeah.
I can never spell Berkeley right
I
the
know,
first
it's actually
time.
Berkeley. Which file do you need open? Was there only one I sent you? I think I sent you a couple, right?
Yeah, right. To the files. Like 4 or 5 files.
That one?
I think so.
Any idea which drawing?
Right, this one.
This plan?
Yep.
So is this structural drawing set? And are these the original drawings or do they have FRP called out?
You
No,
can
this is
search.
the new.
No, you can search FRP to see all of it and highlight to see all of it. Placed
Just one?
there. Just to search all of the.
Sure.
Yeah.
Whoa.
This the box
Check.
above your little bit more. This
On the
is
ribbon.
right.
And
Is
to
it
the
right?
Right. Then
Highlight.
highlight check.
Check it. And then the next page. Yeah, this one.
Okay, so these are drawings where the engineer is calling out shear strengthening on a few walls.
Did you have a specific question, Sing?
No.
Or you just wanted to look at them?
So this is a concrete wall, I think, with FRP on one side.
I think it's more clear when you see the elevation.
Okay.
It's a big project.
It's a big project. And a little confusing too. Aniket doesn't always do a good job of clearly explaining what needs to be done, or
Always.
he sends me files like in 8 different emails and I have to go back and
Yeah.
remember what he told me 2 weeks ago. It's a little hard to deal with.
It's a collection.
Collector strengthening on the roof, I'm guessing this is a roof, yeah.
And this is the level 2.
so they already like decided what needs to happen on all these.
Yeah, it basically just says what design force we need to design to,
Okay.
but yeah.
Yeah, so
They've
the,
already decided like if our P goes exactly here.
Correct.
Wow.
So we're doing the step 1.
we're doing what?
Step 1. Document examination.
Oh, yeah. There we go. So this is still a plan view?
No, this is just your wall elevation.
Oh,
So
okay.
adding trim FRP around openings, they're adding a bunch of, the shear strengthening also, got anchors shown,
Yeah, well, this is more detail than an engineer normally gives us, so
yeah,
it's actually kind of nice.
MAR group, MAR structural design.
Shear transfer, 37.5 kips per foot.
Right.
That's a lot.
Okay.
So if can you go to the last page?
Sure can.
That's the one. That was.
Maybe it's not the last
Cái
page.
giá con đứa lực này thôi.
There was a detail.
Is this the shear transfer?
4, 6.
So I think that steel beam inside the concrete is like an existing collector maybe,
Tại mấy cái con mua đâm vô vào.
Okay.
but anyway. So I think, seeing what you might have to do on this job because the 37 kips per foot for shear transfer is really, really high, we'll have to do mortar ramps to make it, because,
Like the collector.
I don't know why I'm trying to draw in the air, we have a whiteboard in here, I should just go use it. Jesus, doing shuffle every time I walk by. So the way that was drawn before was something like this, and it looks like they've drawn it a little differently now, but, so, if we do our normal shear transfer detail, we basically have our like L-shaped FRP, right? With the 2-inch base radius, but we can only get, after all the reductions, somewhere around 5 kips per foot, so they need 37, so it obviously doesn't work. So what I told Annika is we'd have to do mortar ramps, wherever we need the FRP, and have the FRP go like that. And so because we're not doing L-shaped, we're allowed to design it, I guess the new train of thought is shear transfer way, but
Shear friction.
shear friction, sorry. So that's what we need to do, I think, at that detail to be able to come up with, and we'll probably have to add several layers of FRP to get it to work.
Is that the one that you showed me in the shear transfer trainings?
Friction.
Shear friction.
Convert from tension to.
Yeah, like the
Right.
combination layer of
Yeah, exactly. So the way we've done the calculations in the past are taking the shear equations from ACI 440.2. But what we're thinking would be better than that is to use shear friction calculations, because what we're showing is transfer between the wall on the top and the beam in the middle,
Yeah,
right?
but
That's
the
where we
joint
have
is
shear
here that he
force.
wants to cross with added shear strength, so.
And we can't put any on the outside, it all has to go on the inside.
Good question.
like the ball.
I don't recall. It might say in one of the notes. Have you noticed yet if it says? We should look for that, because if we can go both sides, that would be great.
Because this is what we're looking at, right? Is transferring the shear.
Yeah, there's some weird, it looks like some detail on the outside, it kind of looks tricky to
Oh, yeah.
add on the other side.
It's a theater,
Oh,
and so a catwalk is a little thing, little walkway up in
For
the
cats.
sky.
No, for
I
kitties
got
like
it.
me.
Catwalk. Whoop.
Or be strength where it goes provide 2-inch hole.
So,
What are they doing?
of adding a big collector or something. So 2-inch hole probably for each one of these holes.
Cho biết đặt như thế nào. Để ăn lắm.
But so what is the FRP? I don't know.
So the FRP is probably there for shear strengthening, and then they're adding steel over the top of it.
Wow.
So we have to plan for those penetrations and that. So it looks there like we can do it on both sides, but I'm not sure if that's the case for everywhere. Yeah, Sing, when you get your head more into it, we'll have to probably talk about it.
Same thing.
Very confusing. Whoever, one of them, someone.
Cái shop thì một.
But yeah, so in this case, the engineer put a lot of FRP detail on the drawings, and that's pretty rare.
Yeah.
Usually, there's very little detail, and they'll just on the plan draw a line and say collector 100 kips or something. But here, the engineer's putting details about where the collector strengthening goes and which layer is on top and all that. So it's kind of helpful because we have to make fewer decisions, but also it seems like it's going to be very confusing.
So, was there something else you want to look at on the plans while we have them up? Sing?
No.
No?
What is this?
They showed FRP recessed here. Use that word again. Or depressed.
Bad.
So they want to chip out the concrete,
Looks like it. They want it lower in.
install
Like
FRP,
fabric
and
or
then
laminate? So is that fabric or?
That's the way they showed fabric on plans, so I assume it's just fabric.
FRP bad.
Deep enough into existing, oh, it's a wall, apparently. Is that a plan view?
This is a column. This is a column?
Oh yeah, it says column. So they want it recessed in the wall so that exterior smooth finish.
Oh,
So they want the FRP to basically disappear.
I see.
But
What
we
does that
can't.
last part of it say? Include 5/8 inch half round horizontal joints. Oh. They want those reveals to show up afterwards, I guess. I'm not sure why that's in the FRP note. Maybe they don't want us to fill those in.
Oh.
Like if our FRP needs to be like this wide, they don't want us to fill in the reveal. Ooh, yikes. And then I said, I did hear from Aniket, we are competing for this job still, it's not ours, even though we're doing shop drum. So, because it's DSA, we have to include our design of theirs, so.
But it looks like it'd potentially be a very big job.
Yes, and hopefully we can actually come up with solutions. Because I don't know, some of the shear strengths I don't think are that high, but.
Yeah, the 37.5.
Well, that's shear transfer, but I'm talking about the shear strengthening of the wall itself.
Oh, right, and we can only do one-sided.
Yeah, maybe not, I don't know.
Could you open the Excel file? I think that they gave an Excel file and then it's here, the thing inside it. Just take a quick look and I didn't get it.
Theater.
Whoa.
Oh, so this is compressive strength for the various elements. So, yeah, so the key is ASC 41, so rho is what? Phi is what? 1.0, yeah. And then you just take the average strength. I think one of his emails actually said what he wanted us to use in the design, so I'm not sure you really need this too much, but.
Yeah, so I think the whole point of this sheet is just to give you F prime C.
Yeah.
Okay.
They did a bunch of cores, it looks like.
But there's
And
also.
FY.
Oh, can we use the higher?
I think he said what to use in an email too.
Okay. Yeah, so they gave us all the data, but even I'm a little like I don't know. I think it's weird when engineers give us this information because the engineer needs to assume a value.
Right.
So they can give us 39 values, but it doesn't matter what these are. They need to tell us exactly what to use.
Yeah.
Or if they want us to use different ones for different walls, we could, but usually
No.
no. But usually we don't do that.
So yeah, he was clear, he let us know which to use, but he gave us more data, so.
Yeah.
And apparently I just sent it on. Sometimes I delete stuff you guys don't need, but not this time, apparently.
Rivets. This must be old.
Alright,
That's gonna be, we need to reschedule the project, sub-project for this one, because I think we need more than 3 people on this project.
okay.
So I think maybe tomorrow we'll reschedule the.
Maybe, let's go down and talk about it now, so I can let the people know they're not getting there. Maybe if we, because I think I only scheduled 2 projects that day.
Tomorrow?
Yeah.
Tomorrow we have 4.
Oh, really?
Yeah.
Oh, tomorrow we have 4, but this one's not due till Wednesday?
But tomorrow is due date. But the customer due is
Wednesday.
2 days, yeah, right. Wednesday.
Okay, well, let's talk about it. We can move things around, maybe.
Yeah.
Alright,
Any other drawings questions for now?
Later.
All right.
thank you everyone.
Part 2 tomorrow.
Structural